A city-killer asteroid is heading our way, and we have just years to stop it. This is not a movie plot. It is a genuine threat that planetary defense experts are racing to solve right now. By the end of this, you will understand exactly how humanity is building a global shield to deflect a cosmic impact. We will uncover the secret weakness of asteroids that makes them possible to move and reveal the single most important factor that determines if a deflection mission succeeds or fails. Are we truly prepared to save the world from a danger that once wiped out the dinosaurs? Our solar system is a cosmic shooting gallery, a place of constant motion where ancient rocks hurtle through space on paths that sometimes cross our own. These near-Earth objects, or NEOs, are the leftover building blocks of our solar system, and they come in all shapes and sizes. Some are mere pebbles, burning up harmlessly in our atmosphere as shooting stars. Others are city killers or even civilization-ending behemoths. The stark reality was famously put into perspective by planetary scientist Dr. Amy Mainzer, who noted that the dinosaurs did not have a space program, and we all know what happened to them. That single sentence underscores the immense stakes of our work today. To truly grasp the threat, we need to understand the asteroids themselves. They are not all the same. The most common are the carbon-rich C-types, dark and primitive bodies that are like time capsules from the solar system's birth. Then there are the stony S-types, made of silicate rocks and metals, and the metallic M-types, which are essentially the dense cores of what were once much larger bodies. This composition is not just a scientific curiosity, it is absolutely critical. It dictates both the damage an asteroid would cause and our strategy for stopping it. Think of it this way: trying to push a solid ball of iron is a very different challenge than trying to nudge a loose pile of gravel held together by its own weak gravity. A rubble pile asteroid might absorb the energy of an impactor, while a solid metallic one could be far more straightforward to deflect. The danger of any specific asteroid is a complex equation, factoring in not just its size, but its speed, its density, and the precious amount of time we have between its discovery and a potential impact. How would our world change if we knew with certainty that a significant impact was probable just 1 decade from now? This foundational understanding of the threat is what makes our next line of defense so vital: the global network of telescopes and sensors that scan the skies, giving us that all-important early warning. This global vigil unfolds every clear night, a silent symphony of data collection spanning continents. Giant mirrors in Arizona, sensitive cameras in Hawaii, and radar dishes in California all work in concert, feeding information to central hubs like NASA, a Planetary Defense Coordination Office. Their mission is deceptively simple: to find every single one of those moving points of light before one finds us. The workhorse of this endeavor is often a process called the observational triplet. A telescope takes 3 images of the same star field over the course of an hour. Powerful software then scrutinizes these digital snapshots, searching for any pinpoint of light that has shifted its position against the fixed background of distant stars. That tiny mover is a candidate, a potential near-Earth object on a journey that could bring it uncomfortably close to our home world. Once spotted, the real detective work begins. Larger telescopes are tasked to follow up, gathering more data points to calculate the object's path, its orbit around the Sun. This is where planetary radar becomes an invaluable tool. Facilities like the Goldstone Solar System radar can fire a powerful beam of radio waves at a newly discovered asteroid. By analyzing the signal that bounces back, scientists can determine its exact distance, its speed, and even create a rough image of its shape and size. This transforms a vague orbital estimate into a precisely mapped trajectory. Consider the Catalina Sky Survey, a project based in the mountains of Arizona. Its telescopes alone are responsible for discovering thousands of these objects, a testament to both the scale of the search and the dedication of the teams involved. But this entire system, our first and most crucial line of defense, operates on a knife's edge. What if a crucial patch of sky is obscured by clouds for a critical week? What if a key telescope goes offline for maintenance at the very moment a faint, fast-moving city killer enters its field of view? The reliability of this network is not just about technology, it is about constant, unwavering vigilance. The probabilities of impact are never static. They are constantly refined with each new observation, a number that can spike with initial, uncertain data, and then hopefully plummet to zero as more measurements are made. This relentless pursuit of certainty from the void of space is what buys us the most precious resource of all, time. And time is the one thing we cannot afford to lose when the next step is to actually reach out and touch one of these ancient wanderers. High on a dormant volcano in Hawaii, the Pan-STARRS telescope opens its massive eye to the night, capturing thousands of images in a single evening. Each photograph is a digital net cast into the cosmic ocean, sifting for moving specks of light against a sea of fixed stars. This is the painstaking work of the census, a global effort to catalog every potentially hazardous object that drifts near our world. These ground-based surveys are the silent, unblinking sentinels of our planetary defense, the foundational layer upon which all our hopes are built. They rely on wide-field telescopes, instruments designed not for deep, focused study of a single object, but for scanning vast swaths of the heavens quickly and repeatedly. The goal is simple yet monumental: to find these faint, fast-moving dots before their paths become a direct threat. The data they gather is astonishingly rich. By meticulously tracking how an asteroid's brightness changes over hours or days, scientists can deduce its rotation rate, estimate its size, and even piece together a rough idea of its shape. Is it a lumpy potato, a spinning top, or a contact binary, two rocks gently touching? Every flicker of light tells a part of that story. All this information flows into international clearinghouses like the Minor Planet Center, where orbits are refined with relentless precision and potential impact risks are soberly calculated. But what about the objects that are too small or too dark to be seen until the last moment? For those, systems like a TLS, with its twin telescopes in Hawaii and South Africa, act as a final tripwire. Designed to scan the entire visible sky every night, a TLS provides a crucial last-minute warning for smaller asteroids, the ones that could still unleash devastating regional damage. This raises an intriguing possibility. Could a global network of dedicated amateur astronomers, armed with increasingly powerful backyard telescopes, significantly augment these professional efforts? Their collective eyes, watching from countless locations, could provide invaluable extra data, catching things that might otherwise be missed. The continuous, diligent improvement of these terrestrial eyes is our species' first great step in taking control of its cosmic destiny. Yet, even the clearest mountain air presents a limitation: the blurring effect of our own atmosphere. To see the true hunters in the void, we must eventually rise above it. Even our most powerful ground-based telescopes face a fundamental limitation: the shimmering veil of Earth's own atmosphere. To see the true hunters, we must rise above this blurring filter and station a sentinel in the void. Enter NEO Surveyor, a revolutionary space telescope designed for one singular purpose: to find the asteroids others cannot see. Unlike ground observatories that rely on reflected sunlight, NEO Surveyor will detect the faint heat signatures these objects emit. An asteroid, even a dark and coal black one, is warmed by the sun and glows in the infrared part of the spectrum. This simple shift in perspective is a game changer. It means the mission will excel at locating those stealthy, dark asteroids that are nearly invisible to optical telescopes. More importantly, it completely eliminates a terrifying blind spot, the direction of the sun. Ground-based telescopes cannot peer anywhere near our star's blinding glare, leaving a vast celestial corridor unmonitored. An asteroid approaching from that direction could remain hidden until it was tragically too late. As one mission lead aptly put it, finding asteroids before they find us is a lot easier when you can see them coming from all directions. The goal of NEO Surveyor is both ambitious and precise, to discover at least 90% of all near-Earth objects larger than 140 meters within its first decade of operation. This size range includes the true city killers, objects capable of unleashing continental-scale devastation. The data it returns will be more than just a list of new objects. It will be a comprehensive treasure map of the inner solar system, revealing the orbits, sizes, and compositions of thousands of previously unknown bodies. What other secrets about the primordial building blocks of our planetary neighborhood might this infrared sentinel uncover? This flood of precise information will form the unshakable bedrock for the most critical step of all, the moment we decide to reach out and physically alter the course of a celestial object. Once NEO Surveyor or a ground-based telescope spots a new object hurtling through the void, how do scientists decide if it is a passing curiosity or a genuine threat? They turn to a kind of cosmic traffic light system, a set of scales designed to classify danger from the skies. The most well-known of these is the Torino Impact Hazard Scale. Picture a simple scale from 0 to 10. A 0 means the object poses no hazard at all. Its path will take it harmlessly by. A 10, at the opposite extreme, signifies a certain global catastrophe, an impact so large it threatens the future of civilization. Most newly discovered asteroids start at level 1, a green light indicating a routine pass that merits standard monitoring. The real attention begins when an object climbs to level 4 or 5. This is the yellow light, a situation demanding careful analysis and concrete contingency planning by astronomers and space agencies. It means a close encounter with a real, though still uncertain, chance of impact. Then there is the more technical technical impact hazard scale. This tool provides a deeper, more nuanced risk assessment. It compares the calculated hazard of a specific asteroid to the random background risk we always face from unknown objects of a similar size over the years leading up to the potential impact date. A Palomar scale value of 0 means the risk from this new object is just equal to the background noise. A positive value indicates the risk is higher, demanding immediate attention, while a negative value suggests the risk is lower than the ever-present cosmic background threat. This helps scientists cut through the noise and prioritize which objects truly need more telescope time and urgent study. Now, imagine the global response if an asteroid was suddenly upgraded to a Torino scale level 6 or 7. That is the orange zone, a threatening close encounter with a high likelihood of a regional devastation. At that point, the conversation would shift instantly from scientific observation to active, international planetary defense. Understanding these scales is the key to interpreting the headlines and data that will inevitably flow from our detection networks. They translate complex orbital calculations into a clear, actionable language of risk. But what happens when that risk becomes a clear and present danger, and the scales tip from yellow to a menacing orange? The true danger of an asteroid impact lies not in the initial flash, but in the chilling chain reaction it unleashes upon our world. That moment of contact transforms a celestial traveler into a weapon of planetary scale. The kinetic energy of an object just 1 kilometer wide, moving at tens of thousands of miles per hour, is released in an instant. This creates a fireball hotter than the surface of the sun, incinerating everything within sight. A supersonic blast wave radiates outward, flattening forests and cities across an area the size of a small country. Yet this is only the beginning. The impact blasts millions of tons of pulverized rock and vaporized asteroid high above the atmosphere. This ejected material forms a thick, global shroud of fine dust and sulfate aerosols. Sunlight that should warm our planet is instead reflected back into space, triggering a drastic and prolonged cooling known as an impact winter. Crops fail worldwide as growing seasons vanish. Global food webs collapse, leading to widespread famine. The same plume can also generate intense acid rain, poisoning waterways and soil. The Chicxulub impact 66 million years ago offers a sobering case study. It was not the initial quake that ended the age of dinosaurs, but the enduring darkness and cold that strangled the food supply for years on end. Even the location of the strike changes the nature of the disaster. An ocean impact might spare the immediate blast zone, but it would displace unimaginable volumes of water, sending tsunamis hundreds of feet high crashing into coastlines across entire ocean basins. Our modern civilization, with its tightly interconnected and just-in-time supply chains, is uniquely vulnerable to such a protracted global shock. Could our economic and agricultural systems withstand years without a reliable harvest? This stark understanding of the aftermath transforms planetary defense from a theoretical exercise into a direct investment in the survival of our species. It forces us to ask not just if we can deflect an asteroid, but how we will do it with the clock ticking relentlessly down. The Kinetic Impactor strategy turns a spacecraft into a cosmic cue ball, striking an asteroid with enough force to nudge it off its deadly course. It is a concept of elegant simplicity, relying on the basic laws of momentum we see in a game of pool. When one billiard ball strikes another, energy and motion are transferred, sending the second ball rolling in a new direction. In the void of space, this same principle applies, but on a monumental scale. A spacecraft traveling at immense speed slams into an asteroid. The key is not to shatter the object, but to impart a tiny, precise change in its velocity. This minuscule nudge, perhaps just a few millimeters per second, might seem insignificant, yet over millions of miles of travel, that small change in speed compounds into a massive shift in position, enough for the asteroid to pass harmlessly by Earth instead of striking it. The groundbreaking DRRT mission was our first real-world test of this theory. It deliberately targeted a small moonlet named Dimorphos, which was orbiting a larger asteroid called Didymos. The impact was a resounding success, measurably shortening Dimorphos's orbit and proving that humanity can indeed alter the path of a celestial body. As one mission scientist noted, we are proving that we have the capability to change the motion of a natural celestial body in space. Yet the effectiveness of a kinetic impactor is not a simple calculation. It depends profoundly on the asteroid's composition. A solid, monolithic rock might be pushed more predictably, while a loose rubble pile, essentially a collection of boulders and dust held together by feeble gravity, could behave very differently. The impact might create a large crater and throw a plume of debris or ejecta back into space. The recoil from this ejected material acts like a secondary rocket thruster, adding an extra push to the asteroid itself. This means the momentum transfer is not just from the spacecraft, but from the explosive cloud of debris it kicks up. This leads to a fascinating question. Could a series of smaller, carefully timed impacts provide more control and a greater overall deflection than one single, massive collision? The triumphant success of DRRT gives us our first proven tool for planetary defense, a reliable and technologically straightforward option. But it is only the first and most direct answer to a threat that may demand more nuanced solutions. But what if the asteroid is a fragile collection of rubble where a direct hit could shatter it into multiple, still dangerous pieces? For these delicate situations, planetary defense has conceived a far more patient and gentle approach. This is the Gravity Tractor, a spacecraft that uses nothing but the fundamental force of gravity itself to perform a slow, cosmic tug of war. The principle is beautifully simple. A spacecraft maneuvers to a position near the asteroid and simply holds itself there, hovering using its thrusters. Though the spacecraft's own mass is minuscule compared to the mountain of rock it faces, the two bodies are still gravitationally attracted to each other. That faint, constant pull acts like an invisible tow rope. Over months or even years of this silent vigil, the spacecraft exerts a tiny, continuous force on the asteroid. This gradually adds a minuscule amount of velocity, slowly altering its path. The change is incredibly gentle, just a whisper of a push, but in the frictionless environment of space, that whisper compounds over millions of miles into a massive and predictable course correction. This method completely eliminates the risk of fragmentation, making it the ideal tool for loosely bound rubble piles that would simply absorb the punch of a kinetic impactor. The challenge, of course, is the immense patience and precision required. The spacecraft must have an ultra-reliable propulsion system to maintain its exact position for years on end, constantly making tiny adjustments against the subtle tugs of solar gravity and radiation pressure. Think of it as trying to hold a car a precise few inches from another car while both are racing down a highway at thousands of miles per hour. One practical application would be to use a gravity tractor as a fine-tuning maneuver. A kinetic impactor could provide the initial brute force shove to push a large asteroid out of the immediate impact corridor, and then a gravity tractor could be deployed afterward to make the final, delicate adjustments, ensuring the object is perfectly shepherded into a safe, stable orbit around the Sun. This combination of forceful and gentle techniques gives planetary defense a versatile toolkit. Could a future swarm of small, efficient spacecraft powered by advanced solar electric propulsion work in concert to shepherd an entire family of hazardous objects? The gravity tractor embodies the thoughtful, long-term side of protecting our planet, proving that sometimes the most powerful force is not a collision, but a persistent, gentle pull. For the most severe threats, we must contemplate a tool of ultimate power and profound complexity. Nuclear deflection represents the final option, a last resort for when all other methods fall short. This is not the dramatic asteroid-shattering blast you see in movies. In reality, detonating a nuclear device directly on an asteroid could shatter it into a cloud of radioactive debris, transforming one massive projectile into countless smaller ones still on a collision course. The true concept is far more subtle and scientifically elegant. The device would be detonated at a calculated standoff distance from the asteroid's surface. The intense flash of X-rays and neutrons would superheat a patch of the surface, causing it to violently vaporize. This stream of vaporized material, or ejector, shooting out into space acts exactly like the exhaust plume from a rocket engine. The reaction force from this plume pushes against the asteroid, imparting a steady and surprisingly controlled thrust. This process, called ablation, uses the bomb's energy not for a single destructive shock, but to create a predictable, continuous push. The effectiveness is staggering. For a city-killer asteroid detected with only a few years of warning, or a civilization-ending behemoth a kilometer across, a nuclear standoff blast could provide the substantial velocity change that a kinetic impactor or gravity tractor simply could not achieve in time. A physicist from a national laboratory once framed it perfectly, noting that it is about using the energy to create a predictable thrust, not an explosion. Yet the challenges are as immense as the power itself. The engineering required to deliver and precisely detonate a device in deep space is formidable. More complex are the political and legal hurdles. Launching a nuclear device into space touches upon a web of international treaties and would require a level of global cooperation and trust never before seen. How would the world's nations adapt existing frameworks to permit such an act, even to save the planet? Who would control the trigger? This method remains our most potent theoretical shield, but deploying it would be the most profound decision in human history. This silent and steady push comes from a concept known as the ion beam shepherd. Imagine a spacecraft that does not touch the asteroid at all, but instead uses a focused, invisible jet of charged particles to gently nudge it off course. It is a more advanced and potentially more efficient cousin of the gravity tractor. The spacecraft employs a sophisticated electric propulsion system, the same kind of efficient ion engines that have powered deep space probes on their long journeys. But instead of using its thrust to move itself, the craft aims its engine directly at the asteroid. It fires a constant, precise beam of ions at the surface. Each tiny ion carries a minuscule amount of momentum, and as this stream bombards the asteroid, that momentum is transferred, creating a continuous, low-thrust push. One of its greatest advantages is standoff distance. A gravity tractor must hover dangerously close to the unpredictable gravitational field of a tumbling rock. The ion beam shepherd, however, can operate from a much safer and more stable position farther away. Its thrust can be dialed up or down with incredible precision, and could even be reversed if needed, offering a level of control that physical impactors cannot match. The primary challenge is immense power consumption. Generating a sufficiently powerful ion beam for months or years would likely require an onboard nuclear reactor, adding significant cost and complexity to the mission. Yet this very technology, developed for exploring the outer solar system, might one day find its ultimate, most vital application right here, defending our home world. It represents the cutting edge of planetary defense thinking, moving beyond brute force toward a future of exquisitely controlled, non-contact manipulation. But how do we know which of these diverse tools to use when a real threat emerges? The answer lies in a final, critical reconnaissance step, one that sends a scout ahead to look our enemy in the eye. Laser ablation transforms a beam of pure light into a cosmic tow cable. Picture a fleet of mirror-like satellites orbiting in perfect formation, each concentrating sunlight or an artificial laser onto a single, precise point on an asteroid's surface. The intense heat does not explode the rock, it vaporizes a tiny portion of it, creating a superheated jet of gas and plasma. As this vapor streams relentlessly into the vacuum of space, it acts like the exhaust from a miniature rocket engine, generating a gentle but continuous thrust that pushes the entire mountain of rock in the opposite direction. This is a propulsion system driven by photons, a method of turning energy directly into motion. The beauty of this approach lies in its precision and its potential sustainability. Because the push is so finely controlled, engineers could steer an asteroid with the accuracy of a master pilot, making tiny course corrections over years to guide it perfectly into a safe harbor in space. The power source is equally elegant, massive, lightweight solar arrays harvesting endless energy from the sun itself, making this one of the only truly green planetary defense strategies. One ambitious concept even envisions a permanent directed energy installation, perhaps on the far side of the moon, acting as a fixed sentinel capable of engaging threats from any direction. But the challenges are as formidable as the promise. Focusing a laser beam with perfect accuracy across millions of miles of empty space is a monumental feat of engineering. The target itself is no stationary bullseye. It is a dark, tumbling, and often lumpy object spinning unpredictably through the void. How do you keep a beam of light locked on a single spot when the entire landscape is constantly rotating and shifting? The power requirements are equally staggering, demanding solar arrays larger than any yet deployed. Yet, the potential payoff justifies the immense effort. This technology could one day be our best answer to the most unpredictable threats of all, the long-period comets that swing in from the frozen depths of the solar system with little warning. These icy intruders give us only a few months or years to respond, a timeline where slower methods like gravity tractors are useless. A ready-made laser ablation system, already stationed in space, could spring into action, delivering a sustained push that grows just enough over those critical final months to make the difference between a hit and a miss. It represents a future where our planetary shield is not just reactive, but proactive and permanently vigilant. With so many deflection strategies now on the table, from kinetic impactors to ion beams and lasers, a pressing question emerges. How do the world's space agencies decide which tool to pull from the toolbox when a real asteroid threat is confirmed? That countdown clock is already ticking for planetary defense teams, a silent metronome measuring the years and months until a potential encounter. The moment a new asteroid is spotted, a meticulously planned sequence of events is set into motion, transforming a cosmic threat into a manageable, step-by-step problem. The first phase is the most frantic, a race for certainty. From the instant a telescope logs a moving speck of light, astronomers worldwide begin a coordinated dance of observation. They are not just watching the asteroid, they are hunting for every possible data point to lock down its future path. Each new measurement, from optical telescopes to planetary radar, tightens the noose around its orbital uncertainties. The initial probability of impact might be a frighteningly high number, but with enough data, that number will almost always plummet to zero. But what if it does not? What if, after weeks of intense scrutiny, the probability holds steady or even climbs? This is the trigger. The moment a specific threshold is crossed, official notifications flash from scientific bodies to national governments and space agencies. The world, or at least its leaders, would learn that a risk has been upgraded from a statistical possibility to a concrete threat demanding a response. This launches the most complex phase of all, international consultation. No single nation holds the responsibility or the capability to defend the entire planet alone. Representatives from spacefaring countries would convene, likely under the umbrella of the United Nations, to confront a question never before asked in earnest. How do we, as a species, organize to fend off a danger from the heavens? The choice of how to deflect the asteroid hinges on one irreplaceable factor: the amount of warning time we have. A warning of several decades is a luxury. It allows for a slow, fuel-efficient gravity tractor to begin its gentle, years-long tug, or for a series of smaller kinetic impacts to nudge the object with cumulative precision. But if the clock shows only a few short years, the response must be swift and powerful. A high-energy kinetic impactor, like the one tested by DART, becomes the most viable option. And in the most dire scenario, with a large object and a warning of just months or a year or two, the sobering discussion about a nuclear standoff deflection would move from theory to urgent necessity. Once a method is chosen, the mission itself is launched, a testament to human engineering racing against the celestial clock. Yet even after the spacecraft has done its work, the vigil is not over. Telescopes will track the asteroid for months or years to come, verifying that its new path is a safe one, that the nudge was enough. This entire timeline, from discovery to all clear, is a symphony of global cooperation played under the most intense pressure imaginable. The success of every step depends entirely on the one that came before it, a chain of human ingenuity where the very first link is the most vital of all, the gift of time granted by our watchful eyes on the sky. A unified planetary defense is humanity's ultimate team project. No single country possesses all the necessary technology, funding, or expertise to single-handedly protect the entire world from an asteroid impact. This is not a national security issue, it is a human security issue, a challenge that transcends borders and demands a coordinated international response. The framework for this cooperation already exists, quietly being built within organizations like the United Nations Office for Outer Space Affairs. This office facilitates critical dialogue through specialized groups such as the Space Mission Planning Advisory Group, known as SMPAG. Think of SMPAG as the world's mission control for planetary defense planning. It is the forum where spacefaring nations come together to share data, assess threats, and agree on a single, coordinated deflection strategy. The goal is to prevent a chaotic and dangerous situation where two countries, acting independently, launch conflicting missions that cancel each other out or, worse, inadvertently steer the asteroid toward a different populated region. This collaborative spirit extends to the very foundation of detection. Shared access to the world's telescope networks and radar installations is not just beneficial, it is essential. The precise tracking required to plan a deflection mission relies on a global patchwork of observatories, from Chile to South Africa to Japan, all feeding their data into a common pool. An official from the UN office captured the essence of this effort perfectly, stating that an asteroid impact is a natural disaster we can see coming, and it is one we can prevent if we work together. But this raises a profound question. Are our current international treaties and political institutions strong enough to withstand the immense pressure of a real, imminent threat? When the clock is ticking down and national interests clash, will the spirit of collaboration prevail? This global framework is the indispensable glue that binds our technological capabilities into a coherent and trustworthy planetary shield. These space agencies form the command structure of our global shield, the generals translating planetary defense theories into concrete action. At the forefront is NASA, a Planetary Defense Coordination Office, the central nervous system for American efforts. It does more than just track asteroids. It funds critical sky surveys, spearheads technology development, and serves as the primary liaison for international partners. Its greatest practical test to date was the DRRT mission, a bold demonstration that turned a spacecraft into a precise orbital tool. Across the Atlantic, the European Space Agency, or ESA, plays an equally vital role. Its forthcoming Hera mission is the essential follow-up investigator. While DRRT proved we could hit an asteroid and change its orbit, Hera will fly to the impact site to perform a forensic analysis. It will measure the crater's exact size, analyze the composition of the asteroid, and precisely determine how much momentum was transferred. This data is the missing piece that will turn the DRRT impact from a successful experiment into a quantifiable, reliable technique that can be scaled up for future, larger threats. ESA also operates the Near-Earth Object Coordination Center, a hub that continuously monitors and analyzes risk data for the whole world, but the alliance extends further. Roscosmos brings immense launch capability and decades of spaceflight experience. Japan's space agency, JAXA, has proven its extraordinary prowess with the Hayabusa missions, which successfully landed on asteroids and returned precious samples to Earth. China's National Space Agency, CNSA, is also advancing its own ambitious plans for asteroid exploration and deflection. The key to their effectiveness is a deeply ingrained culture of collaboration. These agencies do not operate in secret silos. They share telescope data freely, co-author mission concepts, and regularly participate in joint tabletop exercises. In these simulations, teams from around the world confront a fictional impact scenario, working through the chaotic days of discovery, decision-making, and deflection under immense pressure. This practice is what builds the trust and procedures needed for a real event. Even a primarily national project like the NEO Surveyor Space Telescope is designed as a global public good, its stream of data available to scientists and governments everywhere. This established ecosystem of government agencies raises a fascinating question for the new space age. How would the entry of a powerful, commercially driven space entity change this dynamic? Could a corporation with its own fleet of rockets and spacecraft offer deflection as a service, and what new partnerships or tensions would that create? The combined engineering might and shared scientific knowledge of these global institutions is the only reason we can even contemplate standing up to a cosmic threat. The authority to move a celestial body is a power humanity has never before possessed, and with it comes a labyrinth of legal and political questions with no easy answers. Who exactly gets to decide to alter the orbit of an asteroid? There is no comprehensive international treaty that explicitly grants this authority or lays out the rules for planetary defense. The foundational document remains the 1967 Outer Space Treaty, which declares space the province of all humankind and holds states internationally liable for any damage caused by their space objects. Yet this venerable treaty was drafted long before asteroid deflection was a tangible possibility. It provides guiding principles but offers no clear instructions for the moment we must actively defend our planet. The legal vacuum is profound. If a deflection mission launched by one country accidentally breaks an asteroid into multiple pieces that then strike different nations, who is held responsible? The existing liability convention would likely apply, but the unprecedented scale of the disaster would strain international law to its breaking point. The use of nuclear explosives in space, a potentially vital tool for deflecting large asteroids with short warning, is further complicated by other treaties like the Partial Nuclear Test Ban Treaty, which prohibits nuclear detonations in the void. Would the threat of global extinction provide sufficient legal justification to bypass these restrictions? The decision-making process in a crisis would likely fall to an ad hoc coalition of the most capable spacefaring nations, ideally coordinated through the United Nations. But the mechanism for achieving a swift, binding consensus under the extreme pressure of a ticking clock remains entirely untested. This leads to a deeply unsettling scenario. Would a single nation be legally or morally justified in acting unilaterally if it perceived an imminent civilization-ending threat and the rest of the world was mired in debate? The technology to deflect an asteroid is meaningless without a robust, pre-agreed-upon legal framework that the entire world can trust. Establishing clear rules for the decision, the execution, and the liability is not a bureaucratic afterthought. It is as critical to our survival as the rockets and the spacecraft themselves. How do you tell billions of people that a mountain is flying toward them without causing mass panic or paralyzing denial? This is the profound communication challenge at the heart of planetary defense. When a new asteroid threat emerges, the initial data is always a cloud of uncertainty. Scientists will know the object exists and that its potential path crosses Earth's orbit, but the exact probability of impact might swing wildly with each new observation. Announcing a 1% chance could be perceived by the public as a 99% certainty of disaster, while downplaying it risks a fatal complacency. The key is a disciplined, unified message. A single, trusted international body, perhaps a coalition of the world's leading space agencies and the United Nations, would need to become the sole source of truth. Their updates would be relentlessly factual, explaining not just the current risk number on the Torino scale, but what that number actually means, what the margin of error is, and what the next steps are for observation. They would have to repeatedly clarify that an upgrade from a Torino Level 2 to a Level 4 is not a sign of impending doom, but a reflection of better data and a more precise understanding of the threat. This transparency is the only antidote to the sensationalism that often dominates media coverage. Headlines screaming about a doomsday rock generate clicks, but they erode the public trust that is essential for a calm, coordinated global response. The communication challenge intensifies dramatically if the chosen deflection method involves a nuclear device. How would officials explain the necessity of launching the ultimate weapon into space to save the planet? They would need to meticulously distinguish the standoff blast concept from the destructive movie trope, emphasizing the physics of ablation and the controlled push over a cataclysmic explosion. Public forums, detailed animations, and candid interviews with scientists would be crucial to demystify the process. Misinformation in this environment could be as dangerous as the asteroid itself, fueling conspiracy theories, causing stock market collapses, or triggering geopolitical blame games that paralyze the international response. Building the necessary trust cannot start during the crisis. It must be built now, through ongoing education and open dialogue about the realities of the cosmic environment we inhabit. The success of a deflection mission may ultimately depend as much on clear, calm communication as on the flawless engineering of the spacecraft itself. The price tag for protecting our entire civilization is surprisingly modest. NASA's entire planetary defense program operates on an annual budget of about $150 million. To put that into perspective, it is a sum dwarfed by the cost of a single modern fighter jet, and it is a minuscule fraction of the global spending on national militaries. This funding pays for the essential groundwork, the telescope operations that find the threats, the research into deflection methods, and the critical international exercises that ensure we can work together when a real crisis emerges. The DRRT mission, a landmark success that proved we can deflect an asteroid, cost just over $300 million to develop and launch. In the world of major space science missions, that is a relatively economical proof of concept. We must weigh these millions against the trillions. A single asteroid impact in a populated area could trigger economic losses measured in the tens of trillions of dollars, a figure that includes not only immediate destruction but the long-term collapse of global supply chains, agricultural systems, and financial markets. The cost of inaction is almost incalculable. Investing in planetary defense is arguably the most important insurance policy our species can ever purchase. The premiums are low, but the coverage is for the continued existence of our global civilization. Beyond sheer survival, the technological advancements driven by these efforts often create valuable spin-offs. The precision navigation required to rendezvous with a distant asteroid, the advanced propulsion systems for a gravity tractor, and the sophisticated sensors for deep space observation all find applications in other space industries, from satellite servicing to future resource mining. Yet this rational economic argument constantly bumps against the short-term nature of political and budgetary cycles. How do you justify steady funding for a threat that may not materialize for a century, when there are so many immediate and visible problems demanding resources today? Are we being dangerously penny-wise and pound-foolish, saving small amounts now while risking a cataclysm that would bankrupt the world? This financial balancing act forces a profound question about our foresight as a species. Are we willing to pay a small, steady price for a secure future, or will we gamble everything on the odds that the sky will not fall on our watch? The most dangerous threats are the ones we never see coming. Beyond the known orbits of near-Earth objects lurk the solar system's true wild cards, celestial ghosts that defy our current detection networks. Long-period comets are the most dramatic of these. They originate in the distant, frozen Oort cloud, a vast spherical shell of icy bodies far beyond Pluto. These comets can spend thousands, even millions, of years drifting in the deep freeze, utterly invisible to our telescopes. When a gravitational nudge finally sends one falling sunward, it accelerates to breathtaking speeds, often over 100,000 miles per hour. By the time its glowing tail becomes visible in our inner solar system, we might have only a few months of warning before a potential close approach. A city-killer comet detected just 6 months out would be a planetary defense nightmare, its immense velocity and short timeline rendering most of our gentle deflection methods useless. Then there are the stealth asteroids, dark and spectral wanderers. These are not solid rocks, but often fragile, carbon-rich bodies so dark they reflect almost no sunlight, making them nearly impossible for optical telescopes to spot against the blackness of space. They are the cosmic ninjas, slipping through our observational nets until their shadow falls across our world. An astronomer's warning echoes here that our greatest vulnerability may come from the direction we least expect. This is the critical blind spot in our shield. How do we find these faint, fast-moving threats with enough time to act? The answer lies in the next generation of space-based observatories, like the NEO Surveyor, which will hunt using infrared heat signatures rather than reflected light. But even that may not be enough for the fastest comets. Preparing for these outliers demands a proactive, permanent presence in space. Concepts for orbital sentinel telescopes, positioned at gravitational sweet spots like the Earth-Sun L1 point, could provide a constant sunward watch. Others propose a network of deep space telescopes stationed farther from Earth, creating a wider net to catch incoming objects earlier in their journey. Deflecting a long-period comet would likely require a standing rapid response team and pre-positioned hardware, ready to launch within days or weeks of a discovery. It would be a mission of absolute last resort, where the immense power of a nuclear standoff blast might be the only tool capable of delivering a sufficient push in such a short, desperate time frame. Confronting these unknown unknowns is the final test for planetary defense, moving us from simply watching the sky to actively patrolling the cosmic neighborhood. The same spacecraft designed to unlock the secrets of distant worlds are also the silent guardians of our own. This is the powerful synergy between deep space exploration and planetary defense, a relationship where every journey outward makes our home a little safer. Consider the recent sample return missions. When OSIR-ISREX gently touched the asteroid Bennu, it did more than collect precious dust. It revealed a world of surprising fragility. The asteroid's surface was not a solid sheet of rock, but a loose collection of pebbles, so porous that a spacecraft landing barely made a dent. This single discovery fundamentally altered our understanding of how a kinetic impactor would work on such a body. The earlier Hayabusa 2 mission to the asteroid Ryugu provided a similar revelation, showing a surface littered with large boulders and a lack of fine regolith. This kind of intelligence is priceless. Without it, a deflection mission might be planned for a solid rock, only to find its impact absorbed by a fragile rubble pile, a catastrophic miscalculation. The very act of exploring these asteroids gives us the blueprints we need to defend against them. The technological advances required for these ambitious scientific voyages are the same ones that power our planetary shield. The sophisticated ion propulsion that carried the Dawn spacecraft to the asteroid belt could one day provide the steady, efficient thrust for a long-duration gravity tractor mission. The autonomous guidance systems that allowed a rover to land itself on Mars are the precursors to the AI that would enable a kinetic impactor to steer itself toward a tiny, distant asteroid at thousands of miles per hour. Even the powerful deep space network of radio antennas, which pulls faint signals from the edge of the solar system, is the same communications backbone that would allow us to control a deflection spacecraft in a moment of crisis. This two-way street of benefits is profound. A future mission to deflect a non-threatening asteroid, a test conducted on a real solar system body, would be a scientific bonanza. The impact would act like a cosmic hammer, cracking open the surface and exposing the pristine material within, allowing us to study the interior composition of an asteroid for the first time. We would learn not only how to save the world, but also about the original ingredients that formed it. This leads to an exciting possibility. Could a future lunar base established for exploration and research also serve as an ideal platform for a planetary defense observatory? The Moon's far side, permanently shielded from Earth's radio noise and with long, dark nights, would be a perfect location for powerful telescopes to continuously scan the depths of space for those faint, fast-moving threats that are so difficult to spot from our planet. The connection is clear. Our ambition to explore the cosmos is not a distraction from protecting Earth. It is the very foundation of that protection. Every new world we visit teaches us more about our own, and every technology we develop for the journey quietly strengthens the shield around our pale blue dot. This digital lifeboat is already scanning the ocean of data, where artificial intelligence sifts through the noise to find the faint signals that matter. Every clear night, our global network of telescopes generates a staggering flood of images, millions of star fields that would take human eyes centuries to scrutinize. Artificial intelligence trained through machine learning now performs this Herculean task in real time. It has learned to spot the subtle signature of a moving asteroid, distinguishing it from the static pinpricks of distant stars, the streaking trails of human satellites, and the false signals of electronic noise. This is not just about speed, it is about perception. An AI can detect an object so faint and fast-moving that it might slip past even the most experienced human observer, catching threats that would otherwise remain hidden in the data until it was too late. Once a new object is found, the role of artificial intelligence shifts from discovery to prediction. The future path of an asteroid is not a simple arc. It is a complex dance influenced by the gravitational pull of every planet it passes, and even by the subtle, continuous push of sunlight itself. This is the Yarkovsky effect, where the uneven heating of a rotating asteroid by the sun acts like a tiny, persistent thruster, slowly but surely altering its orbit over decades. Artificial intelligence can run thousands of orbital simulations in minutes, each one factoring in these minute forces to map out a cone of possible futures for the asteroid. This allows scientists to understand not just the most likely path, but the entire range of possibilities, providing a far more robust and rapid assessment of the true risk. As one data scientist involved in this work noted, "We are drowning in data, and AI is the lifeboat that helps us find the needles in the haystack." This computational power could even extend to the Deflection mission itself. Imagine an AI tasked with planning the perfect kinetic impact. It could model the asteroid's composition, its rotation, and its internal structure to calculate the ideal point of impact, the precise angle and speed needed to transfer the maximum amount of momentum and steer the object clear of Earth. This moves us from a simple push to a perfectly executed orbital maneuver. The logical endpoint of this integration is a profound question. Could we one day deploy a fully autonomous system, a network of smart telescopes and pre-positioned interceptor spacecraft, capable of detecting a threat and executing a deflection without any human in the loop? The trust we place in these intelligent systems would have to be absolute, but the speed they offer could be the only answer to the very fastest of incoming threats. The sterile glow of a conference room screen illuminates the faces of the world's top planetary defenders. They are not watching real data, but a carefully crafted fiction designed to save us all. This is a planetary defense tabletop exercise, a high-stakes game where the pieces are nations and the board is the solar system. Organized by space agencies like NASA and ESA, these simulations drop participants into a detailed, evolving scenario of an incoming asteroid threat. The parameters shift in real time, mirroring the uncertainty of a real discovery. A new observation might suddenly double the estimated size of the object, or a failed telescope might create a critical data blackout. The participants, a mix of scientists, engineers, and emergency managers, must navigate this chaos. They practice who to call, what data to share, and how to make agonizing decisions with incomplete information. In one recent simulation, the fictional asteroid had a 72% chance of striking Earth in just 6 months. The exercise did not focus on building a spacecraft, but on the political and logistical pandemonium that would erupt. How would governments prioritize evacuation zones? How would they manage global panic and the inevitable spread of misinformation? The lessons learned are often uncomfortable, revealing critical gaps not in our rockets, but in our policies and international protocols. These exercises build something as vital as any piece of hardware: the muscle memory for global crisis management and the personal relationships that allow for swift, trusting cooperation when every minute counts. What if a future simulation introduces an asteroid that is not one rock, but a tightly bound binary, requiring 2 simultaneous deflection missions? Regularly stress testing our human systems in this way is the only guarantee they will hold under the ultimate pressure. Deep within research labs and on the digital drawing boards of engineers, the next generation of planetary defense is already being sketched out. These are not just refinements of existing ideas, but radical new concepts that approach the problem from entirely different angles. One of the most elegant proposals involves something as simple as a can of paint. The theory suggests that by sending a spacecraft to coat an asteroid with a layer of highly reflective white powder, or perhaps a dark black substance, we could fundamentally alter its thermal properties. This taps directly into the Yarkovsky effect, the same subtle force that slowly pushes asteroids over eons. A white surface would reflect more sunlight, reducing the heating effect and the resulting thermal thrust. A black surface would absorb more heat, amplifying the push. It is a method of turning the sun itself into a gentle, continuous tractor beam, using nothing but physics and a carefully applied coat of pigment. The challenge, of course, is covering an entire mountain in paint. a logistical puzzle that would require innovative robotic sprayers or perhaps a cloud of released particles that would settle evenly across the surface. Another concept seeks to supercharge the gravity tractor. An enhanced gravity tractor would not rely on its own modest mass alone. Instead, the spacecraft would first land on the asteroid, use robotic arms to capture a massive boulder from its surface, and then lift off again, holding that multi-ton rock. By adding the asteroid's own mass to the spacecraft, the gravitational pull between the two bodies would be significantly strengthened. It is a clever form of cosmic jiu-jitsu, using the asteroid's own material against it to create a far more powerful and efficient tug. Then there are the proposals for mass drivers. Imagine a robotic device that lands on an asteroid and begins to systematically mine the rock and soil beneath it. Instead of storing this material, it loads it into a powerful electromagnetic cannon and fires it off into space at tremendous speed. Every chunk ejected is like a tiny rocket exhaust, with the reaction force pushing the entire asteroid in the opposite direction. This method is the ultimate in sustainability, using the asteroid itself as its own propellant tank to fuel a long-duration deflection. Some of the most visionary ideas involve solar sails. These vast mirror-like sheets could be used in two distinct ways. They could be positioned to physically push against the asteroid, using the faint but constant pressure of sunlight. Alternatively, a fleet of sails could act as a giant sunshade, positioning itself between the asteroid and the sun. By casting a precise shadow on the surface, the sails could create a temperature imbalance, once again harnessing the Yarkovsky effect to steer the object without any physical contact at all. Could we one day see a permanent network of these solar sails stationed at strategic points in the inner solar system? A reusable and always on-call defense infrastructure ready to intercept any new threat that emerges from the darkness. These blue sky concepts ensure our planetary defense toolbox will never be complete, but will constantly evolve, offering future generations an ever-expanding menu of options to safeguard their world. Behind every algorithm and every telescope lens is a person staring into the night, driven by a quiet understanding of the stakes. These are the scientists and engineers for whom planetary defense is not just a job but a vocation. Their work is a marathon of meticulous detail, not a sprint toward glory. The astronomer at a remote observatory endures the biting cold for a 10-hour shift, methodically collecting the 3 images of a star field that form the observational triplet, her focus absolute because a single blurry frame could mean missing a crucial data point. The mission planner spends years perfecting the trajectory for a kinetic impactor, running thousands of simulations to account for every conceivable variable, from solar radiation pressure to the asteroid's unknown internal structure. Meanwhile, the policy expert navigates a labyrinth of international treaties and diplomatic sensitivities, building the fragile consensus that would be necessary for a global response. Their shared motivation is a profound sense of guardianship, a duty to ensure that the story of life on Earth does not end with a sudden, preventable period. They are building a shield not for themselves but for generations they will never meet, working on timescales that span entire careers. Their greatest triumph would be a silent one, a perpetual state of readiness where the big deflection mission is always just a plan on a desk, a simulation in a computer, a spacecraft that never needs to launch. What kind of resolve does it take to dedicate your life to a problem that, with immense luck, may never need your final solution? It is a unique blend of optimism and pragmatism, a belief that humanity can shape its own destiny, paired with the sober acknowledgement that it must. The most critical component in our planetary defense arsenal is not a specific technology or a treaty, but the enduring passion and perseverance of these individuals. They are the human embodiment of our will to survive, the quiet sentinels ensuring our world remains a world with a future. Our journey through planetary defense is ultimately a story about human determination. It reveals a species no longer content to be a passive passenger on a cosmic raft, but one actively learning to steer. We have built a global network of eyes on the sky, developed a versatile toolbox of deflection methods, and begun the difficult work of forging the international partnerships necessary for a unified response. The central lesson is clear. The challenge is no longer a matter of if we possess the basic capability, but how well we have honed our skills, funded our efforts, and organized our global response. While no defensive system can ever be flawless, the progress of the last 2 decades is nothing short of revolutionary. We have moved from theoretical models to a proven technology, having successfully altered the orbit of a celestial body in deep space. We have a clear and actionable path forward. The ultimate shield is not merely a telescope or a spacecraft, it is the collective will of humanity to safeguard its only home. This shared responsibility demands our continued vigilance and investment, a promise we make not to ourselves but to all the generations yet to come. We would love to hear your perspective on this grandest of human endeavors. Share your thoughts in the comments and subscribe to join us as we continue exploring the technologies that are shaping our future.